welcome back. So we have been discussing this MIMO architectures for FR1 and FR2. Okay. So we'll mostly finish discussing this. Some leftover will be there. We'll cover it in the next class. So what is we recap this whatever we learned about FR1 MIMO. We have seen FR1 in all the glory, okay, in all in detail. But what are we saying here? Some of the key aspects which will make it different from FR2 MIMO implementation. Okay, that's what we are trying to capture here. Okay, right. So this 100 megahertz bandwidth is available, which is shared across multiple users, which needs to be shared. Okay, right. And what does this impose? What kind of constraint it is imposing? That you need to design a fully digital architecture, MIMO architecture, wherein each and the receiver or the transmitter has access to the digital signals corresponding to each of the antenna. Right? Okay, fine. So, and with that, with the flexibility you have, you can design anything. Right? You can design different precoders for different users. You can design different precoders across different PRBs. Okay, so if the channel is changing across PRBs or within PRB, you can design different precoder. Right? Okay, and we are able to do that because you have access to complete digital data corresponding to all the antennas. Right? Okay, so that you can digitally combine these signals, whether you want to design a precoder which has amplitude variations, which has phase variations, okay, you can do all that. Okay. So now in this case, basically, so you have single user MIMO, which is used to increase spectral efficiency or the rate of the users by transmitting multiple layers to each of the user. Okay, right? But the users are orthogonal in frequency. Okay, that is single user MIMO, right? Okay, that on each PRB you transmit different users data and do MIMO for each one of them, right? Okay, then the single user MIMO is used to increase the system spectral efficiency. And then what are we saying here? That the users are multiplexed in antenna domains spatially in addition to this. Okay, so what are we saying here? This is not single user MIMO, this is multi-user MIMO. Okay, that's a typo. Okay, so this should be multi-user MIMO. Okay, multi-user MIMO. Okay, what are we saying here? So what are we doing here? We are multiplexing user over each PRB. Right? What is here? What is happening in single user MIMO? That you consider different users on different PRBs, right, and do MIMO for them, correct? And then in this multi-user MIMO, which what do we do? You take different transfer block of different users, multiplex them, and then you send them on the same PRB, right? Okay, that's multi-user MIMO. Okay, so users are multiplexed they are called like spatially multiplexed. Now you are multiplexing them not on frequency, you are multiplexing them on the spatial domain or in the precoding domain, right? Okay, so this is used to increase the system spectral efficiency because you are able to support multiple users on the same PRB, right? Okay, so whatever architecture we have studied till now is mostly applicable for FR1 because of these constraints, that you should be able to process data of different users, you should be able to have access to signals from all the antennas so that you can design precoders for different users, you can design precoders for different PRBs, okay, right? So this is the key idea, that this is typically, you have to do it for FR1 because the bandwidth is low, you have to support large number of users, you have to provide higher data rate for each one of them. Okay? And so what are we saying? Base stations usually have large number of RF chains. And in fact, the examples which we considered, number of RF chain is equal to number of antennas. Right? 64 antennas, 64 RF chains. Right? And at the transmitter, each RF chain consists of 2 DACs, 1 up converter, right, 1 power amplifier. At the receiver side, what does it consist of? Each RF chain, 1 low noise amplifier, 1 down converter, and 2 ADCs, right? So each antenna is connected to its own RF chain. Okay, and users typically have 2 to 4 RF chains and antennas, okay, right, if it is a fully digital architecture. Now, you see this, where did we do the precoding? Precoding is done in the digital domain before taking the FFT. We are doing it in the frequency domain, right, okay, and that too digitally, right, because we have that flexibility. You can do it over each PRB, you can do it over for different users, okay. Now, having seen this, okay, what are we saying here? Let's come to FR2, okay, which is also known as millimeter wave, okay. What are we saying? Channel bandwidth of 400 megahertz is available, okay, minimum, okay. There is maximum 400 megahertz. But typically, you get each operator gets 400 megahertz for millimeter wave system, okay. First difference, okay, this multi-layer MIMO, okay, the single user MIMO with multiple layers is not used in FR2, and for the reasons which we have already discussed, because the bandwidth is large, okay. Why are we doing all this? So that we can increase the data rate of each user. Why are we doing multiple user MIMO? Why are we supporting more than one user on each PRB? So that the total data rate increases. You can support more number of users, right, with higher data rate, correct. Now, all these has typically been done because of the bandwidth constraint, okay. I am repeatedly saying that, okay. When the bandwidth becomes large, okay, the intention is to provide higher data rate which can be done without doing all this multi-layer, multi-user MIMO, okay, and you will see that that is how the FR2 systems are designed, okay. So, but they have their role, okay, even for FR2 system these multiple antennas have their own role, and what are they used for? They are primarily used to combat hostile millimeter wave channel, okay, right, because the channel becomes very poor over there, okay, a signal cannot travel for a longer distance, just for example, okay, right, and you do not have this constraint, but you have another constraint, okay, right. So, what happens there is that these multiple antennas we use to combat this channel, and how do you do that? You form sharp beams towards the user, okay, I will show you how that happens, okay, I will give you a pictorial view. So that if the beam is sharper, okay, then it will travel a longer distance, okay, and that is the primary objective of using multiple antennas there in FR2, not this, okay, right. Once this is objective, you do not want to do multiple layers, you do not want to do multiple users, okay, right, then you do not want access to all the signals, digital signals from all the antennas, because this operation I will show you can be done in the analog domain itself, okay. You do not really have to go to digital domain, okay, if you do not support this, okay, right, then you can come up with simpler architectures, MIMO architectures, wherein you do not have to do all this, okay, your multiple antennas will satisfy this objective, which is basically to combat this channel, okay, right, and this is what you want to do, okay, right, and you see this, that this multiple antennas, even for FR1, even if you had multiple, even if you had a single antenna at the receiver, at the user, you could live with that, because it will basically be able to receive NL is equal to 1 layer, right, okay, and the channel is not hostile there, okay. So, it will receive good data rate, okay, but here when the channel is hostile, users are forced to have multiple antennas, okay, because the channel is so bad that users also need to have multiple antennas to combat for that channel, okay. Now, here we spoke about 1 or 2 antennas, here you will see that user also needs like 4 to 16 antennas, because the channel is so bad, okay, right. Now, if users are also using large number of antennas, where is the user handset is this small, where will you put those 16 RF chains, right, okay, that is a constraint, okay. So there is a need to come up with simpler architectures. That's what we'll see for millimeter wave systems, because this constraint is not there, okay, most of the time, and this constraint is there, okay, and with this constraint, user also definitely needs to have multiple antenna, not only two, more than that, so that it can combat this channel, okay. So now the channel is so bad, if you see that initial FR2 system, now people, by the way, okay, so this FR2 system are typically deployed for line of sight scenarios. Well, if channel is so poor that the signal transmitter is not even able to cross cross one wall itself, okay, right. So you typically see that whatever deployments are there for line of sight, and what are the example use cases in stadiums, okay, wherein like people are watching a match and everybody is uploading the data. But if you see, we have installed a millimeter wave base station, okay, and the users are sitting, and they have a line of sight link, correct. That's a use case of millimeter wave system, okay. Another one is malls, wherein like, or forget malls, auditoriums, okay, wherein again people are watching a concert and then they want to upload some data, right, okay. So, and this is because otherwise FR2 is still not successful for non-line of sight systems, okay. All the deployment which you see in US, India, there is no deployment currently, okay. They are typically for the two use cases which I have shown it to you, okay, right. And the reason is the channel is hostile. So what are we saying here? The multiple antennas, okay, what are they primarily used for? As I said, by forming sharp beams toward the user, okay. Or, so what are we saying here? There will only be one rank, NL is equal to one layer will be transmitted, okay, correct. We don't care about multiple layers because of this, okay. What are we doing here? Base station has 256 antennas, user has 16 antennas, okay. Base station forms a small beam, a sharp beam towards the user, okay. Then user also, because it has 64, when it has multiple receive antenna, it can capture the signal and it can form a receive beam. That's what I am showing you here, because it is, what is this beam I am showing you? The receiver which will design, W receiver, right, because multiple receiver will combine the signal, okay, and we display that using the receive beam, okay, because the signal is being received from multiple antennas and you are capturing the signal from multiple antennas to form a sharp receive beam. Similarly, the signal from multiple antennas at the transmitter is being transmitted for one layer and a sharp beam is formed towards the user, okay. I am shown these beams, it finds out where is the user, that is what it indicates. So, it will not transmit on these beams, it figures out that the user is located here. So, it will form a beam in this direction, user will capture the data by designing a suitable receiver W. It will do MRC because only one layer is being transmitted, right. I just showed you that example which we took where for rank 1 or rank 2 transmission, right. Rank 1 calculation, what did we do? W was designed, right. So, same W will be designed here, okay, right. But the key idea over here is these multiple antennas are primarily for forming sharp beams towards the user, okay. So, both base station and user need to form sharp beams. I have explained it to you why, okay. The user also, because the signal becomes so poor, channel is so bad, even though base station has formed a sharp beam, because the channel is so bad, again the signal will be low. So, user will have to form its own receive beam to capture this signal which is coming from all the directions, from all the direction mean all the antennas, okay, right, okay. So, what am I saying here? If the user has one antenna, the system is not going to work, okay. So, this indication, it shows us that user is basically combining the signal from multiple receive antenna to form a beam like this, okay. So, base station and user should have similar number of large antennas. Typically, this is an exaggeration, okay, but users, if base station will have 256 antenna, user needs to have large number of antenna. You take it with a pinch of salt, okay, but what am I saying here? That user also needs to have a large number of antennas, okay, typically 4, 8, 16 in order for this to work, okay, because channel is so bad, okay. And if that is the case, okay, we need to have simplified millimeter wave MIMO architectures, okay. If let us say there is another fact, okay. So, this is one millimeter wave. Now, if you look at it, each antenna is placed at a distance of lambda by 2, right, okay, that is the usual usual antenna spacing. Now, when you go to higher bandwidth, lambda reduces, okay, right. So, your antenna size will also come down, even though you have, so that is good, because you can design antennas in a small patch, correct. So, your patch will only be this, you can put it on one side of the mobile, okay. It is not like FR1 where it will have a huge dimension, lambda is like 10 times, if it is like, what is that, 3 gigahertz and 30 gigahertz, so lambda increases by 10 times for FR1, okay. Now, antenna size has come down by a factor of 10, okay. Even if you want to put, let us say 10 RF chains over here, you cannot put, because there is no space to do that, right, on the UE and on the UE side, okay. Each RF chain, you remember 2 ADCs, right, one RF up converter, one low noise amplifier, each one of them is going to occupy space and each one of them is going to guzzle a lot of power. Your mobile will run out of battery in no time, correct, okay. So, if you have to basically the current technology, okay, wherein you cannot have so many like integrated RF chains on a single chip, okay, you need to have simplified millimeter wave system, okay. It is primarily because of the technology, right. If you can design a system, a sophisticated system at like with, you can put a 16 RF chain in one small chip, right. Why won't you design, you will use millimeter wave MIMO here also, I mean multi-user MIMO here also, you will further increase the data rate, right, okay, you can do that, nobody is stopping you from doing that, okay. But there are like technology constraints primarily, okay, right, because 16 RF chain, so much of power. So, I need to design an RF chain not only in small space, it should consume minimal amount of power to make it successful for a system like this, okay. So, the constraint, these are the constraints, okay, that you need to have 12 millimeter wave MIMO design, okay. So, what is happening, okay. So, what am I showing you here, okay, you look at this, that as I said, this multiple antennas are being used to sharpen the beam towards the user, right. How is it happening? I will show you a picture, okay. This is one antenna. So, the signal radiated from one antenna, you look at that, what have I plotted? The signal strength from 0 to 180 degree, because there is a one antenna system, signal is radiated in all the directions, okay. With a two antenna system, and look at the gain is 1, okay. This is the gain, that is what I have plotted, correct, okay. And I am talking about this picture, if I am showing, this is only for line of sight channel, okay. Non-line of sight channel, this picture does not hold, and we are talking about FR1 for line of sight implementation only, okay, right. So, this is, if you have two antennas, I mean if you do this like combine, maybe I am talking about transmit, this is at the transmitter, okay, two antennas, and you do combine the signal properly, you get this, look at this, the gain has become from 1, it is close to reaching 1.5 and signal is becoming sharper in a particular direction. This is omnidirectional, you are radiating the signal in all the directions. Here you are radiating the signal in a particular direction, okay. 4 antennas, look at this, gain is becoming 2, signal is becoming further sharper. Look at this, 8 antennas, okay, right, signal is becoming more sharper and gain is also increasing, reaching 3. Look at 64, look at this is called pencil beam, right, the gain has become 8, okay, and look at this in a particular direction. And what are we saying? That for FR2 you want to do this, right, okay. This is line of sight channel, you transmit a signal like this with large gain, correct, okay. And what are we saying? We do not want to transmit multiple layers here, I will transmit over 400 megahertz, I will transmit a signal like this, I will get done, right, okay. If I am interested only in that, what are the architectures which can be supported, right? Okay. So that's what I'm going to show you. So what is happening before we see how this is done? Okay, just a quick recapture of FR1. You take IFFT, you take DAG. This is digital domain. You can do all this in digital domain. Just a recapture. Okay. So pre-coded signal, single layer data. If it is single layer, you do VK XK. For multiple users, is mapped to different subcarriers. This is done digitally. Okay. Channel HK changes across K because of frequency selectivity and multiple users. Right. Even if it is single user, as I said, it is 100 megahertz channel. Channel will change from sub PRB to PRB. So you need to design a different precoder. If it is different user, then of course different users will have different channels. So you'll have to use a different precoder. Right. Okay. So recapturing. So precoder V in principle can change across subcarrier, and your digital system allows you to do that. Fine. Okay. Now, as I said, okay, that you cannot afford this for FR2 because you cannot have 64 antennas and 64 RF chains, right? So I'm going to another extreme. I'll show you one example. We'll take one example wherein there are 64 antennas, only one RF chain, okay, right? One RF chain connected to 64 antennas using some devices in between which are called phase shifters, okay. We are going to consider that architecture, okay. So what are we saying here, okay, that look at this architecture, the digital architecture can help us in designing a system wherein channel is changing across subcarriers, correct, okay. Now if it is a line of sight channel for which FR1 or for which FR2 is being designed, channel doesn't change across subcarriers. It's a frequency flat channel, okay, if it is a line of sight system. And that's our use case, correct. So why did I show you this? Look at the use case for which I am designing the system. I am specifically interested in designing millimeter wave system for a line of sight scenario wherein I am saying that channel doesn't change across subcarriers, okay. So I don't have to design a separate precoder for each of these subcarrier. For the entire band, my precoder can be constant, right? One relaxation. Another relaxation, I don't want to support multiple users, okay. Fine, I want to give 400 megahertz to single user, okay. So I don't have to do multiple layer, okay. I don't have to do multiple users. So I don't have to change the precoder across multiple PRBs. So this precoder can be same across the entire band. If I consider this a simple system like this, wherein I am supporting one user in entire 400 megahertz band, okay, right. So I don't have to do multi-user, and since I am designing it for line of sight system, I don't have to change precoder across the PRBs because channel is flat, right, okay, fine. This is my requirement. Now keeping this in mind, how do I design my system, right, okay. And as I said, we have to design a simplified system because we cannot put so many one RF chain per antenna, okay, and the constraints are, we have discussed that, okay. So what am I saying here now? What kind of a system I am considering? I am considering a system with a single user and frequency flat channel, okay, right. Why? Because I am designing my system for a line of sight channel, plus I am considering a single user system, okay. So what happens? Look at this. What is the first change I have done? Okay, there is no multiple layers, it is only a single layer transmission. V is vector V. I have made this V constant across the subcarriers. That's the system I am designing, because my precoder need not change across subcarriers. Why will a precoder change across subcarriers? For two reasons. One is channel is changing, but for line of sight channel doesn't change. Point number one. Another reason why channel will change is if you are supporting multiple users across PRBs, right? You are multiplexing user. That also I am not doing. Fine. So this precoder can be constant across the entire band. Please understand that of 400 megahertz, right? Okay. You see the first change, and this is a crucial change in implementing an architecture, a simple architecture. Okay, fine. Let's understand then. And to begin with, okay, what am I saying here? Let me simplify it further. This is, I am considering one RF chain and one antenna as of now. I will increase it to like as many antennas as you want. Okay, but first I have simplified it by considering only one RF chain and one antenna. Fine. Okay, we are interested in one RF chain and hundreds of antennas. Okay, because this is a simplified architecture. Okay, I can have only one RF chain. I can increase the number of antennas. Fine. Okay, and I am interested in, I have to pre-code. I have to do this pre-coding. What will this pre-coding, even before we talk about this, why is this pre-coding necessary? Please understand that, okay? Why is this pre-coding necessary? Because of this. Let's go back. This. You have 64 antennas, right? You will pre-code the signal to combine, right? See, base station has 64 antennas. How are you forming this sharp beam? You are combining the signal, correct? And then forming a sharp beam, right? And what is this? This is basically the MRT. That's what it is, right? Okay, fine. So this is, so you need to pre-code, okay? But what am I saying here is, this pre-coder for the system which we are considering is constant for the entire band, right? Is this clear? Okay. Pre-coding is crucial, because without pre-coding, how will I use multiple antennas at the transmitter side? Similarly, combining is necessary at the receiver side, because I have to form that receiver beam also. Okay, right? So pre-coding is necessary, that's why we are pre-coding, otherwise there is no need to pre-code. But key difference is that pre-coder is constant across the entire band for the system we are considering. Okay? So from here to here, this is only for some time, okay, that one antenna. What happens? X tilde k is, because it is for one antenna, okay. So this is also scalar, this is also scalar, this is also scalar, right? Okay, this exercise is a one-step exercise. So, and another thing is, I am considering phase only precoder, okay, e raised to, so what will it be if it is a phase only precoder? I am simplifying this, okay, phase only precoder e raised to power j theta, right, okay. And if it is a phase only precoder, we saw that with the code books, it can give you the maximum gain, it can combine the signal, right, okay, and we can realize maximum gain, okay. So that is, this will stick to, okay. So what have we done? Precoder is constant across all the subcarriers. This assumption, one RF chain and one antenna, okay. So V into X of k, okay, and I am saying that V will be phase only precoder, okay. This assumption I will relax, okay, we will stick to this, okay. So what are we saying? Now, earlier in the last slide, where was this precoding being done? Digitally before taking IFFT, right? Where were you doing this? IFFT, before taking IFFT, everything was done digitally, then only you took the IFFT, right? Precoding is followed by n-point IFFT in transmitter. What does it yield? Okay, so this is, I am considering this signal, please. This is a signal I am considering, okay. If I take, this is, what is this? One RF chain and one antenna, okay, seesaw system. What am I saying? I will take, what will I do? I will take the IFFT of this, right? This is, K is the subcarrier, correct? That is what we do. Once you have done this processing digitally, okay, what will I do? I will take the IFFT of this. What is IFFT? K is equal to n-point IFFT, K is equal to 0 to n minus 1, X tilde k e raised to power j2 pi k IFFT. That is what it is, right? Fine, okay. I substitute X tilde of k. What happens? E raised to power j theta into X of k. This is what it is, right? This is what I have written. Fine, okay. Look at this, e raised to power j theta. Is it a function of k? K is what? Subcarrier. I made it independent with respect to subcarrier, right? Precoder V is independent of the subcarrier. I can pull it outside this summation, right? Okay. What is this? This is IFFT of the unprecoded signal. Okay? Correct? What is this? This is a time domain signal multiplied by the precoder in time domain, not in the frequency domain now. Okay? how am I able to do this? Because my precoder is constant across subcarriers. And why am I able to do that? Because I am assuming single user and line of sight system. Okay, fine. So this is for one antenna, right? So what is this? X of n is the endpoint IFFT of data symbol, which is independent of the precoder, right? Okay, e raised to power j theta, correct? Okay, done, right? Now what happened? What will it enable me to do? Okay, look at the system. There are no multiple users. There are no multiple precoders. Correct? Okay. What happens there? Take the IFFT. No precoding also. Time domain symbol, CP addition, you get the analog signal. Fine. Okay. This will help me. Okay. So what is happening? We have moved the phase only precoding from frequency to time domain. Right? Okay, by assuming frequency flat channel and by allocating entire bandwidth to a single user, right? Okay, phase shifting, this phase shifting I showed, this is the baseband signal. I can equivalently move from baseband to RF also. Okay, I am not showing you that operation, but that can also be done the way I have done this. Okay, right? This is e raised to power j theta x of n still in the is a baseband signal. I can move this phase shifting operation from baseband to RF also, okay, right. So I'll stop here. Okay, so what have we done now? What have I showed you in this by doing this exercise? Okay, that for this kind of system I can do my precoding in the analog domain after taking IFFT, and that too in RF, right. So what was the constraint here? Okay, that I have to basically, for the FR1 system, I had to do all this operation digitally, okay, because multiple users, right, and the channel was even for a single user, channel was changing across subcarriers. Okay. If I relax that constraint, I am able to move this precoding operation from digital domain to the analog domain. Okay. What will I do then? That is where we will discuss in the next class. Okay. This I have done for single antenna. I will show you that this operation is applicable for multiple antennas also. Okay. So what are we doing? If you look at this here, e raised to power j theta, this is the phase of the first antenna. Now if I have two antennas, I do not have the slide, I thought I will not have time. You will have e raised to power j theta 1 x of n plus e raised to power j theta 2 x of n. Okay. So entire precoding operation can be done entirely in the using analog components. Okay. So you need, what am I saying here? Your RF chain, you will need only one RF chain. You can have as many antennas as you want to. Okay, and then can still form a very sharp beam towards the user. Okay, because you just need to do this digitally, x of n, not this. Okay, right. Once you do that, you live with one RF chain, you can add as many antennas as you want to, and then you can keep forming as many sharp beams as you want. Well, not as many sharp beams, you can form a very sharp beam towards the user, right, and that is the intention, okay, for a millimeter wave system. So I will stop here. Okay, we will finish this in the next class, and then I will spend some time on the initial access part. Okay, thank you.